Welcome to Section 3, in which we discuss samples and the relationship with populations. Let's get right into it. In this section, we will highlight the difference between treatment of a sample and a population. We will introduce the important concept of inference and how it links samples and populations together. We will discuss estimation of probability from sample data, as well as summarizing datasets using summary statistics. And finally, we will return to inference so that we can jump into our fourth and final section of this lecture. The distinction between populations and samples is crucial. Often samples are what you have and populations are what you want to know. The population is the entire group that you want to answer questions about. However, it may be unknowable. What you're often doing is taking a sample, which is a part or a subset of that population, and using the statistics of that sample to estimate quantities in the population, which are called parameters. An example of the difference is on the Mississippi River at Vicksburg, Mississippi. There exists some population of all annual maximum flows on the Miss at Vicksburg, but it's an unknowable collection of flows because we can't observe it forever. We only have a sample of annual maximum flows through the National Water Information System hosted by the USGS. Even though we want to answer questions about all the annual maximum flows, we only have a limited sample to work with. Inference is the art of making predictions about a population using a sample taken from that population. We want to know it all, but we're limited by the data that we have. Our sample is made up of representative observations of our population being studied. What we have to do is use that data to answer questions about the population. This process of asking and answering questions about the population is known as inference. The probability of an annual maximum flow over 12,000 CFS is a population parameter. The problem is, we can't see every single annual maximum flow that has happened or will ever happen, so we can't wrap our arms around the population. It would be easy to count all the flows over 12,000 CFS and divide by the total number of flows to get the probability of a flow over 12,000. However, we might only have a small collection of observations because, for example, the USGS stream gauge was only installed 35 years ago. In the case where our data are limited, we could take the data we have and try to make an inference about the population. In our example, we said a gauge had been observing annual maximum flows on the river in question for 35 years. We could take our sample and split it, take each year that had a flow less than 12,000 CFS and put it in the bucket on the left, and take the ones greater than 12,000 CFS and put them on the right. When we do that, we find that there are 25 years less than and 10 years greater than. This means in our sample, we saw that 10 out of 35 years, or 29% of flows, were greater than 12,000 CFS. Remembering our definition for probability, we recall that successes divided by the total number of trials gives us an estimate for probability. Therefore, we estimate the probability of a flow greater than 12,000 CFS being about 0.29. What we did was we used our sample of 35 flows to make an inference about a population parameter, which is the probability of a flow greater than 12,000 CFS. And we inferred that the population value is about 0.29. Of course, in our inference, we're making a few assumptions. The most important one is that the sample we have is representative of the population. In some circumstances, it can be difficult to ascertain whether the sample is representative or not because the population is completely unknowable. For surveys, where people are polled for their opinions, the sample can be checked for representation by comparing the demographics of the respondents in the sample to the general population demographics to see how representative a sample is. For stream flow, if we have limited record of flows, we would have to look at other variables such as climate to tell us if the period containing our sample is a good representation of the entire population. The other major assumptions fall under the IID acronym. These assumptions have to do with the way that the observations that make up the sample were taken. We want the observations to be independent of one another, that is, that they're not dependent on each other in some way. We also want them to be identically distributed, which is similar in nature to the representative sample assumption. Think of identical distribution as the assumption that the samples are coming from the same population. We rely on the definition for long-run probability to estimate probabilities from our sample data. However, this definition is dependent on a limit, that the sample size approaches infinity. In dealing with finite samples, we refer to the proportion of successes to trials as the relative frequency. It might also be called a sample proportion. Using the relative frequency to estimate the probability of an event is an example of making an inference about the unknowable population. So far, we've looked at Bernoulli random variables. An event either happens or it doesn't, or as in our coin flips, heads and tails. Most of the time, we're not interested in things that are this simple. Our random variables can often take on a larger number of values than just yes, no, or heads, tails. A die roll is a simple extension of this idea. A fair six-sided die, when rolled, will produce an integer value between 1 and 6. Each roll of the die is independent of the last, and we can roll a die as much as we like. So let's roll a die 100 times and tally up the number of times each face comes up. We record those outcomes in a histogram, with the height of the bar corresponding to how many times each face, 1 through 6, comes up. You could tell from the chart that 1 came up the most often and 2 came up the least. If you total up the height of the bars, it will come to 100, which is our sample size. If we want to know the relative frequency of each face, we can take the height of each bar and divide it by our sample size of 100. On the right side, we see the scale of the bars changes where we've computed the relative frequency, but that the relative heights of the bars are the same. The histogram on the right side shows the proportion of each of our outcomes in a sample. It describes how each of the outcomes is distributed within the sample. For example, just over 20% of the outcomes were 1, and just over 10% of the outcomes were 2, and so on. The blue bars are the relative frequency for each of the outcomes, 1 through 6, from 100 rolls of a die. We know from physics that a fair die produces each of the outcomes with a probability of 1 over 6. This value is shown as the red line on the plot. In our 100 rolls, we notice that each outcome does not occur exactly 16.6% of the time. In our sample, the proportion of 6s is pretty close, but 1, 2, and 3 are not as close. This discrepancy between what we expect, which is the true value, and what we got, which is the sample value, is called the sample error. Why do our sample values vary compared to the true value? Recall our definition for long-run probability. In a sample, we run a number of trials, which is n. In all of those trials, we count up the number of times our event A happens. Then, we divide the count of the occurrences of A by the sample size n. Long-run probability assumes that we'll get to the true value in a sample with a size that approaches infinity. When we have a small sample, we haven't done enough to shake out the small random variations that cause the discrepancy between the sample and the true value. The smaller our sample size, the larger our sample error is. The larger the sample error, the less confidence we have when we make an inference about a population from our sample. Let's beef up the experiment a little bit. Here is a count histogram and a relative frequency histogram of 1,000 rolls of a fair six-sided die. Notice how the variability in the counts is still present, but visibly smaller than in the 100 rolls case. On the right side, we see that the relative frequencies of the outcomes are all closer to our expected proportion of 1 over 6. We continue on to 10,000 rolls of the same fair six-sided die. Luckily, I don't have to actually roll the die, and I can use computers to simulate the process. Here we see the counts on the left side and the proportions on the right side, again with our 1 over 6 target drawn as a red line. Even at 10,000 rolls, there's still some variation, but it's smaller than the 1,000 rolls histogram and much smaller than the 100 rolls histogram. What these repeated experiments show us is that the quality of our estimate for the population distribution of values is dependent on how big our sample is. The sample error we have is expected to decrease as we have more and more samples. The plot here shows a measure of error for a series of experiments, starting with 10 rolls and going up to 100,000 rolls. The actual value of the error is unimportant, and what is important is that we see that the error in estimating the proportion of outcomes decreases with increasing sample size, just as we would expect. Cumulative frequency is another way of expressing event outcomes. We build cumulative relative frequency from our typical estimates of relative frequency. While relative frequency expresses the proportion of trials that turn up exactly some value, cumulative frequency expresses the proportion of trials that turn up some specified value or less. Relative frequency is used to estimate the population probability that a random variable takes on some specified value, which is written in this way: P of big X equals little x. Cumulative relative frequency is used to estimate the probability that a random variable takes on a value that is less than or equal to a specified value, written as P of big X less than or equal to little x. The well-trod example of relative frequency is the number of times you roll a 4 out of the total number of rolls that you make. A similar example for cumulative relative frequency is the proportion of rolls that are 4 or less out of the total number of rolls that you make. For dice, this means the proportion of times you roll a 1, 2, 3, or 4 out of the total number of rolls that you make. On the left is our familiar histogram computed from 100 rolls of a fair 6-sided die. The height of each bar is the proportion of outcomes that had that exact roll, 1 through 6. On the right is a cumulative frequency histogram computed from the same set of rolls. The bars represent a different event now. Each bar represents the proportion of rolls that turned up that value or less. In other words, it accumulates from left to right. The height of the first bar on the cumulative histogram is the same as the first bar on the relative frequency histogram. However, the height of the second bar on the cumulative histogram is the sum of the heights of the first 2 bars of the relative frequency histogram. This is because the bar represents the outcome 2 or less, which contains the events of rolling a 1 and rolling a 2. The third bar, which has the outcome 3 or less, contains the events of rolling a 1, a 2, or a 3. So as you move rightward on the cumulative histogram, you accumulate events. The last bar has a relative frequency of 1. That's because the outcome 6 or less contains all the possible events, rolling a 1 through a 6. We can compare our relative frequency histogram and cumulative frequency histograms to our expected outcomes. The left histogram has the 1/6 ideal proportion drawn over the top with a red line. On the right, in the same way we accumulate the heights of the bars, we can also accumulate the expected proportions. Complementary cumulative frequency is a method for looking at ranges of outcomes, but in a different way than the regular cumulative relative frequency. If cumulative equates to less than or equal to, then the complement of that is greater than. Cumulative relative frequency estimates the probability of a random variable being less than or equal to a value, but the complement of that is the probability of a random variable being greater than a specified value. Going back to last section's discussion of probability rules, we know that A and its complement are mutually exclusive and exhaustive. Something that happens can either be an A or an A complement, but it can't be in both and it can't be in neither. This means that the complement to less than or equal to has to be greater than and not greater than or equal to. An example of cumulative relative frequency is the proportion of rolls resulting in a 4 or less on a die. This contains the outcomes 1, 2, 3, and 4. The complement to that, which is the complementary cumulative relative frequency, is the relative frequency of rolling greater than a 4, which has the outcomes 5 and 6. Here are 3 views of the same sample containing 100 die rolls. On the left is the relative frequency for each of the 6 outcomes. In the upper right is the histogram we get when we look at the cumulative relative frequency. The first bar contains the roll of 1, the second bar is 1 and 2, the third bar is 1, 2, 3, and so on. The lower right histogram is the complementary cumulative histogram. The first bar contains the rolls of 2, 3, 4, 5, and 6. The second bar contains 3, 4, 5, and 6, and so on. An important feature of the 2 charts on the right is that the sum of the heights of the bars are all equal to 1. This is due to the definition of the complement. The first bar on the top right contains a roll of 1, and the first bar on the bottom right contains rolls of 2, 3, 4, 5, and 6. Since nothing else can happen other than those 2 things, the total probability between those 2 bars has to be 1. Notice also that the last bar in the histogram on the lower right is 0. This is because there's no way to roll higher than a 6 on a 6-sided die. The flip side of this is shown in the histogram above it. The event of 6 or less contains the rolls 1, 2, 3, 4, 5, and 6, which is everything, so it must have a probability of 1. The sample histogram we've been creating has another name, an empirical probability distribution. Let's break down that name. The key is that we call it empirical because it comes from experimental trials and is built using data we've gathered. A probability distribution is a method for telling us how much probability each of our outcomes has. So put together, we have a description of the amount of probability each of our experimental outcomes has. We know from physics that our die produces each outcome with a probability of 1/6. This tells us how much probability each outcome gets. This is our population probability distribution. When we get to section 4 of this lecture, we're going to talk more about the role of probability distributions in inference. But for now, it's good to know that our mapping of outcomes to probabilities is called a probability distribution, and we can construct one empirically using a histogram. Instead of looking at the proportion of specific outcomes in an experiment, we could start to look at properties of a sample as a whole. Often we want to summarize what a sample looks like with measurements we can compare across samples. Sample statistics are numerical measures of a sample that describe its shape. Most of the time, we're interested in measuring a few specific properties. The most important is the central tendency, in other words, where the middle of the sample is. Another important property is the spread or the dispersion of the sample, which describes how spread out data in our sample are relative to the center. Another important but less commonly used measure is a measure of symmetry, which tells us if the shape of the data tends to be the same on both sides of the center. There are several ways to measure central tendency of a sample. The most important is the mean, but the median and mode are also important measures. The mean is the first moment of the sample. It's also the center of mass. It's a probability-weighted average of all of the outcomes. The median is the point where 50% of the data are on either side. For symmetrical distributions, the mean and the median are the same. You can compute it by sorting the data from smallest to largest and then dividing the sample in half. If the sample size is an odd number, there will be a data point in the middle where there are the same number of observations above it as below it. This is the median. For sample sizes that are an even number, you'll have two numbers in the middle. The median is the average of those two numbers. The mode is the most frequently occurring value. For discrete data, this might be pretty simple to compute. You find the value that occurs the most often. For continuous data, it's harder. You might construct a histogram of the data and find the middle value of the tallest bar. You could construct a kernel density plot and find the value corresponding to the tallest part of the density plot, like in the image above. You could fit a parametric model, in other words, a probability distribution, and get the distributions mode. Data can have multiple local maxima, which is called being multimodal, but in general, we won't deal with data like that here. Here is an example of computing the arithmetic mean from a sample of 100 die rolls. For each outcome, we multiply the value of the die roll by the fraction of the die rolls that turned up that value. Then, we add up those products. The result is in the bottom row of the last column, and it's 3.38. On the last slide, we computed the sample mean by looking at the proportion of each outcome in a sample. We can also compute it by looking at each data point in the sample as an equiprobable observation. Equiprobable means same probability. The formula shown on the left is the familiar formula for the average. Applying this formula, we would add up all 100 values we rolled on our fair six-sided die and then divide by 100. Dispersion describes the amount of variability or spread in a data set. Usually, it expresses the amount of distance there is between data points in the sample. The most common measure of dispersion is the sample variance. It's defined as the average of the squared distance of each data point from the mean of the sample. The n over n-1 term at the beginning is referred to as Bessel's correction, and it's important for making inferences about our population. Also commonly used is the sample standard deviation, which is simply the square root of the sample variance. It's useful because it has the same units as the data being measured, whereas the variance has units of the square of the data units. On the right is a histogram showing two samples with the same mean of 100. The red histogram has a standard deviation of 10, and the blue histogram has a standard deviation of 50. The blue histogram is more spread out than the red one, so it having a higher standard deviation makes sense. We can compute the sample variance using the general variance formula on the last slide. Again, this is computed using the tabulated outcomes and their proportions. Note that we have to compute the sample mean first in order to get to the variance. This occurs in column 4, just like the computation we did a few slides ago. There's an additional pair of steps on the right side to get to the variance that depend on that value. The sum in the lower right has to be bias corrected, which is based on our sample size. The factor is shown in the lower left. The resulting mean of 3.37, variance of 2.66, and standard deviation of 1.63 are shown on the bottom. Remember that the standard deviation is computed as the square root of the variance. Just like the mean, we can compute the sample variance from a collection of equiprobable data points in a sample. We still have to compute the sample mean first. Then, for each observation, we subtract off the mean and then square it. After adding those up, we divide by n-1, which is the return of Bessel's correction. This produces our sample variance. The sample standard deviation is still just the square root of the sample variance. The symmetry of a sample can be measured with a statistic called the coefficient of skewness. We look at the symmetry of the data relative to the mean of the sample. It's defined so a perfectly symmetrical sample has a skew of 0. Symmetry becomes apparent when we look at the histograms on the right. Skew values that are negative tend to have a long tail pointing towards the left. Skew values that are positive tend to have a long tail pointing towards the right. If they were symmetrical, they would look more like the dashed part of the figure. Skew divides off a power of the variance in order to make the measurement dimensionless. It also has some business at the front end involving n, which gives it better properties for inference. It's similar in principle to Bessel's correction, which is for variance. The mean, variance, and coefficient of skewness fall into a category of sample statistics called moments. They get that name from similar quantities used in physics. The mean is the first moment. It's pretty straightforward. The variance is the second central moment. It's the second moment due to the fact that we're squaring, or taking the second power of the observations. It's a central moment because we're subtracting off the mean, or centering the variable, before doing the squaring. The skew is the third standardized moment. It's also a central moment. It's the third moment due to the fact that we're cubing the observations. It's a central moment because we're subtracting off the mean before cubing. Finally, it's a standardized moment because we're dividing off a power of the standard deviation in order to make the measurement dimensionless. We're taking a minute to discuss moments because they're an important part of inference that we're going to discuss in part 4 of this lecture. The diagram of inference returns. Now that we've worked with samples for a bit, we can start to think about how we'd use those observations to ask and answer questions about our population. One way of doing this is by assuming that our observations are representative of the population and that we can use sample statistics as estimators for population parameters. For example, we might assume that our measurement of the sample variance is a representative measurement of the population variance. When we go back to our fundamental assumptions that the sample we have is representative of the population and it was taken in a way that is independent and identically distributed, we find that our sample statistics are estimators of population parameters. Here we use the little hat accent to indicate that something is an estimator. First, we see that our sample relative frequency is an estimator for the population probability of event A occurring. Our best guess at the true value of the probability of event A occurring based on our sample is the relative frequency of A. We could take this further to the moments we defined just a bit ago. The symbol mu is used for the population mean, and mu hat means an estimator of the population mean. We use the sample mean as an estimator of the population mean when our sample meets the assumptions. The same goes for population variance, written as sigma squared, and for the population skewness, written as gamma. This is going to be an important basis we use for building probability models of our population in the next section. We've completed our review of the distinction between populations and samples and introduced the concept of inference. We will build off the inference concept in the final section to build models of our populations based off the information that we've got in our samples.